afternoon, everyone. I'm Dr. Jessica Benthuysen. I'm a physical oceanographer at the Australian Institute of Marine Science, AIMS. So AIMS is Australia's tropical marine research agency, and we have 3 locations here in Perth, and then Darwin, and our headquarters are in Townsville. And we also have 2 research vessels. So here is the RV Solander, which is going to be used in some of the field campaigns in Tide. So I'm in theme 1, characterizing the marine environment using sparse and uncertain data. Today, I'm going to be talking about marine heat waves around Australia. I moved to Australia in 2010, and I'd only been living here for less than a year when a marine heat wave occurred offshore of here, where many fish and invertebrates died, as well as seagrass and kelp. So I'm going to be sharing what I've worked on over the past decade, and also what we've learned. So marine heat waves can occur. Marine heat waves can occur through a number of different processes. So some of the drivers that can lead to marine heat waves are shown in the schematic on the left. And then they can have a range of different impacts on the marine environment. So that's shown on the right. So both atmospheric and oceanic processes can lead to a buildup of heat in the upper ocean. And those processes can also be modulated by climate modes of variability, such as ENSO. And those climate drivers can enhance or reduce the likelihood of a marine heat wave occurring. Usually it's compounding factors which are actually contributing to a specific event. And we see a whole range of different impacts on the marine environment, all throughout the food web, and affecting our foundational habitat forming species, but also having effects on fisheries and aquaculture. So how do we define a marine heat wave? Well, in early 2015, I came here to the Oceans Institute for a workshop where we had oceanographers, ecologists, atmospheric scientists, and climate scientists gathered together to define what is a marine heat wave. We came up with this definition that a marine heat wave is a discrete, prolonged, anomalously warm water event at a particular location, and specifically when sea surface temperatures are above the 90th, seasonally varying 90th percentile over at least 5 days. And so with this definition, we can get a set of metrics. So the marine heat wave intensity, or the temperature anomaly above the climatology, as well as the duration, how long those conditions last for. And that also allows us to define marine heat waves, not just in summer, but also in winter time. And this definition is provided in a number of codes. So here you can find it available through this GitHub, coded in Python. Now, a couple years later, we defined another set of metrics, the marine heat wave severity, as well as the category. And that's dependent on the extent to which temperatures exceed the 90th percentile SST above the climatology. So here we have a range of different category levels from moderate to extreme. And a category is the maximum severity reached during an event. And what this metric allows us to do is to start to compare different marine heat wave events around the world and for different years. So I'm going to be using these different metrics: intensity, duration, severity, and category in this talk. Now, we published this recent review on marine heat waves. And as you can see, there is a number of different notable events that have occurred in recent years. And it's not only the temperature anomalies that were reached, which makes them notable, but really their effects on marine life. So for example, in the Mediterranean, this event affected rocky reef communities, corals and sponges. Off the Northeast US, this marine heat wave led to impacts on the lobster fishery industry because the lobster Fishing peaked earlier than usual owing to the warm temperatures, flooding processing plants and driving down prices. And in the Northeast Pacific, this event actually lasted for 2 years and affected the whole food web and led to deaths in many different kinds of marine species. And in the East China Sea, we've had successive marine heat waves affecting their sea cucumber industry. So in this presentation, I'm going to be focusing on these marine heat waves that have occurred around Australia. And the ones I've focused on in particular were off Western Australia in 2011, in the Tasman Sea, and in the Northern Australia and Great Barrier Reef and Coral Sea. And so there have been other marine heat waves that have occurred since then, but these are the ones we're going to focus on. So in summer 2011, we had this very famous now marine heat wave occurring off of Western Australia, known as the Ningaloo Nino. And in fact, this term marine heat wave was coined by the late Alan Pierce from this event. And here we're looking at results from a ROMS model simulation, looking at the sea surface temperature anomalies and surface elevation anomalies, the contours, compared to 2009 and 2010. So the top panels are showing that warm SST anomalies building up along the shelf regions, peaking by early March and then dissipating from March through April. So we can see that the contours are showing this higher sea level near the coast, and then we find this development of anticyclonic eddies, bringing some of this warmer water offshore. We also can look at this evolution of the temperatures off WA through the IMOS moorings. So we're looking at both the meridional velocity at the top and then the temperatures. And we find that there were very strong southward flows during this time. So velocities reaching 1 meter per second, and that's contributing to this warm tropical waters being brought down south along the coast. So the goal of this study was to understand what were the mechanisms contributing to this buildup of heat and this evolution in temperatures. So one of the things that we did with this model was to construct a temperature budget for the region off WA, where we looked at the change in temperatures from January through March over the top 60 meters. We can look at how the temperature changed owing either to advection or air sea heat flux. And during 2009, 2010, we had some amount of warming owing to what you might expect seasonally. But near the shelf regions, we typically have the Capes current at that time and upwelling. So we have that cooler signature. But in 2011, we see that pronounced marine heat wave. So that very warm waters over the shelf. And that was primarily driven by advection. And we can show that quantitatively by taking a control volume and averaging over that region to find that warming was primarily caused by the poleward advection of heat, by the Lewin current, and then a smaller component from air sea heat flux. And in this study, we further identified why the Lewin current reached such intense speed. So in part from remote forcing by equatorial easterly wind anomalies. So that's associated with the La Nina during this time. But also there was a local weakening of the southerly winds, and that really allowed the Lewin current to intensify over this time. So after this study, I actually moved up to Townsville, and soon after, another remarkable marine heat wave occurred, this time in the Tasman Sea. And by this time, we had that marine heat wave framework, so we could actually identify when this marine heat wave started, peaked, and ended. And this was a remarkable one because it lasted for such a long period from September through May of 2016. And it reached intensities of almost 3 degrees. And with this anomalous event, there was a number of different observations. So out of range fish species off of Tasmania, there was also impacts on aquaculture and fisheries locally, and impacts on giant kelp forests. So we can use a combination of both daily temperatures, but also monthly temperature products to examine this marine heat wave. And this time series is illustrating the number of marine heat wave events leading up to this time, but really the red is indicating that this was the most intense event on record. And there were a number of temperature records, long-term temperature records collected around Tasmania through the University of Tasmania and also from IMOS, so the IMOS Maria Island National Reference Station. And again, we can use this marine heat wave approach. And we find that through this in situ data, indeed 2016 had the most intense and longest marine heat wave in their record. And using the Maria Island velocity data, so that's located in the lower corner here, we found that this pronounced warming was related to southward flows at this time. So it's really the East Australian current extension intensifying, bringing this warmer water southward along the coast. And again, we can use an ocean model, this time ocean maps, and construct a temperature budget, and to determine that primarily this marine heat wave was caused by poleward advection and the smaller component from air-sea heat flux. Now, after this event, there was another marine heat wave in the Tasman Sea in 2017. And that one had a very strong impact, especially around New Zealand. And so by this point, there was this growing awareness that we needed to continue monitoring the Tasman Sea for marine heat waves. And by the following year, we had funding to use a new capability. So by 2019, we had funding through IMOS for event-based sampling, which has been going on for three years now. And this project aims to monitor marine heat waves with slocum gliders and is led through the IMOS Ocean Glider facility here at UWA. And this project is a multi-institution collaborative approach toward monitoring marine heat waves using gliders, and gliders have been shown to be an ideal instrument for monitoring marine heat waves in the shelf environment because they can be mobilized fairly rapidly and deployed and out sampling the waters for 3 to 4 weeks. So the gliders can sample a range of different variables and send that information back in near real time. So we had two of these gliders out during this Tasman Sea marine heat wave. And this picture on the right is showing just how we can start to think about combining the high resolution data available from the gliders, as well as complementary data from reanalysis or other ocean modeling products. So now we're going to move to the tropics. And there is a marine heat wave across northern Australia, which is very well known because of the extent of coral bleaching and other impacts on marine life that occurred. So this is a map showing the extent of coral bleaching in a range of different environments. So certainly along the Great Barrier Reef and into Torres Strait. Then there were the first ever observations of coral bleaching in Northeast Arnhem Land by the indigenous peoples. And then there was coral bleaching observed in some of the remote coral reef atolls, such as Scott Reef off the Northwest. Now, if you recall from a couple slides ago, where I showed the seasonal mean temperature anomalies, that Tasman Sea marine heat wave really stands out. And within this color palette, you don't actually see evidence of this strong thermal stress that actually occurred in the tropics at this time. So we can take a closer look into what's actually happening more locally across the north. And the map at the top is showing the maximum sea surface temperature during the summer months. And then each of these different regions are showing the sea surface temperature anomalies and their evolution over a number of years. So in the Indonesian-Australian basin, on the left, top left, we found that the marine heat wave really started in spring 2015 and built up into summer. But by January 2016, a marine heat wave had emerged in all of these other regions as well. And the summer marine heat wave reached a peak in around March for many of these regions and was associated with the longest one on record. And we found that it was related to the very strong El Nino conditions at the time with reduced cloud cover and weakened winds. Now, interestingly, there was a second marine heat wave occurring later on in winter. And for many areas, that was actually the most intense marine heat wave on record. That was in part related to the extremely negative Indian Ocean dipole occurring at that time. But in many of these cases, we see this very rapid transition from neutral or even cooler temperatures in the springtime to this peak in summer when temperatures usually reach their annual maximum. So there's other products we can use to compare against these sea surface temperature analyses. So there are a number of locations around Australia where we do have that long-term in situ records. So these are just some of the examples here from Darwin, off Groote Island, in Torres Strait and Lizard Island. In many of these cases, you see that in 2016, it was the longest and intense one on their record, and less so as you look along the East Coast, certainly across the north. And we have other data available to us, for example, through IMOS Ships of Opportunity sensors on tropical research vessels. We have our thermosalinographs on the Ames research vessels. And that data is collected in near real time and sent back hourly. So we have that data. And this is an example during the marine heat wave, where in this study, we were comparing the ship underway data with the satellite products, and we could identify when the ship was actually in marine heat wave conditions. Now, since this study, we have actually higher resolution temperature climatologies available to us. And the one in particular is a Sea Surface Temperature Atlas of Australian Regional Seas, or the STARS climatology. And if you go onto IMOS Ocean Current, you can actually see that ship underway data compared against this product. So you can see as the ship is moving, what is the temperature anomalies? What are the percentiles? Is that water actually in a marine heat wave? So there's definitely been some progress in recent years in capturing those near real-time temperatures. So finally, we're going to move to the East Coast, and we're going to be looking at these marine heat waves that have occurred in the Great Barrier Reef and Coral Sea. So in 2016, 2017, 2020, where we've had these 3 mass coral bleaching events in only 5 years. And in 2016, you can see that the Torres Strait, the far northern and northern sectors were greatly affected by coral bleaching. In 2017, it was more concentrated in the central to northern regions, but in 2020, you can see that bleaching was found over a very wide extent along the GBR, including some of the southern reefs, which hadn't bleached before. So we've recently completed a project through the NESP Tropical Water Quality Hub, Project 4.2, to characterize some of these marine heat waves. And this is just some of the results that we found looking at sea surface temperature products where we're looking at the temperature anomalies in the Great Barrier Reef Marine Park and the Coral Sea through these different marine heat waves. And so we're looking at just 2016, 2017, 2020 here, but all the results are in the report. And what was remarkable about 2020 is that you can see for the whole of these regions that the temperature anomalies reach this strong severity over a great number of days. So 10 days for the GBR, 16 days for the Coral Sea. And that is far surpasses what we saw in these past events. And in fact, these the magnitude of these anomalies, they peaked in mid-February in the GBR when temperatures typically reach their maximum. And then for the Coral Sea, it happened in early March. So through this, we can actually start to see to what extent this thermal stress affected such a large portion over these regions. And also you can see that there is that, again, very rapid transition from neutral to cooler conditions in December, and then this quick buildup of heat through January. Now we've also compiled the in-situ temperature data from the 2016 and 2017 mass coral bleaching events, and you can find that available through the eAtlas. Now, through this project, we also did a study to understand how well the Bureau's seasonal prediction system forecasted this marine heat wave event. So this is the Axis S1 seasonal prediction system, and that came online in 2018. So in this case, we're just looking at the observations of the marine heat wave severity at the top from every week from February through to mid-March. And again, for the Great Barrier Reef, the severity peaked in mid-February, and for the Coral Sea, it peaked in early March. And when we look at the Axis S1 ensemble mean temperature anomalies and severity, we find that for the earlier start dates from 1st of February, 8th of February, it really didn't capture that buildup of heat. So it underestimated what was eventually going to happen. But certainly it did represent well the initial week predictions. And in this case, you can see that some of this marine heat wave structure did persist out to several weeks, but again, it didn't quite capture that buildup of heat. So this study is currently under review, and happy to talk about that again another time. So finally, another area of my current research is to understand the subsurface temperature variability in the Great Barrier Reef, and especially this region, the central GBR, where there's a number of reef passages which connects the Coral Sea into the GBR lagoon. And what's remarkable about this region is that you get this intrusive upwelling occurring. That's upwelling that flows up along the bottom through these reef passages, and you don't actually see that in the sea surface temperatures. So we're going to look at that here from the eReefs model. So on the left, you see the sea surface temperatures, and then on the right is bottom temperatures. So we're going from spring into summer, and you see that buildup of temperatures near the surface. But at the same time, you get this episodic cooling events occurring along the bottom through the reef passages. And you don't really see that reflected near the surface. So this was during the 2016 marine heat wave. And this cooler water can flow in, but it can also flow back out through downwelling. And you can get a number of wind events coming through, leading to very well-mixed stratification in some areas. And by April, this time, the southeasterly trade winds tend to pick up, and then you have very reduced stratification. So some of my current research is to understand the mechanisms driving this, the upwelling, downwelling through these reef passages, setting the temperature structure during these coral bleaching events. And combining that with information from the IMOS slocum gliders that sampled through the marine heat waves at this time. So that's the middle panel where the gliders are able to navigate through these reef passages in this environment. And we can combine that with information from the long-term IMOS moorings. So there's one located at the outer Palm Passage. And if you're interested, we have an earlier study looking at this intrusive upwelling in the central GBR. So in summary, over the past decade, we have made a lot of progress in identifying and defining marine heat waves and their mechanisms and their ecological impacts. And all of this work is really aimed at developing a better understanding of why these marine heat waves are occurring so that we can actually start to predict where they will happen next, and also develop an understanding of that temperature structure, not just at the surface, but also with depth and at different spatial scales. So one of the goals really to use all this knowledge to be able to build models of marine heat waves into the future. Thank you.
Nobody's volunteered, but we can just get people to talk about stuff. So I'll say we have I was trying to catch you today, I didn't have a chance. Yeah. So I'll say we're doing it. I'll try and make it 12, but I'll see where I get from the. Yeah. You've been finishing like 12:30 or so.
Depends. Last week I was there to run it to one because they really wanted to talk about assignment stuff a lot. I think if they do that, then I'm sort of there to one, other than that, I'm certainly 12.
You know?
Yeah.
That's two. All right. Okay, so let's time for one or two questions, if there are any immediate questions.
I have a question, Phil, for Jessica. That's all right.
Yeah, please.
Hi, Jessica. Yeah, my name is Andrew from University of Wollongong. Thanks, great talk. That was really interesting. I just have one small question. When you talked about gliders and research vessels, is there a strategy when they go out and monitor sea surface temperature, or is it just random movement?
Oh, excellent question. So for some of our observations, like for example, the ships, that's as it's called, ships of opportunity. So usually those field plans are set, weeks, sometimes months in advance, and so the ships are just collecting that temperature data along with those trips. Certainly, sometimes those trips are actually targeting things like looking at the effects of coral bleaching and things like that. So maybe the ship will be out at the same time, but certainly that's opportunistic. The gliders here operated through IMOS UWA. Now those either follow a regular schedule, or as I mentioned, we have this initiative, the event-based sampling, where we are actually trying to with other models as well, trying to pull our knowledge together, try to predict maybe where marine heat wave will occur, and actually aim to deploy a glider to monitor those temperatures specifically.
Thanks, that's very useful. Thanks, Jessica.
I'm interested in the difference between the advection during heat waves and the just because of the role that turbulence plays in those, and auxiliary, how it makes that worse ecologically for the organisms, because the auxiliary factors flow and the water gets clearer from so the radiance gets higher. So there's a lot of auxiliary factors in low turbulence effect, there's advection effect. Is it hard to disentangle those?
I think when we're looking at a very specific location, it can be quite challenging to untangle that. I mean, certainly here in these studies, we're kind of looking out for a very broad scale to get a sense of the different roles in those cases. And certainly in areas of the boundary currents, that's where we're finding intensification of the flows can contribute to the advective driven marine heat waves. But that's, yeah, so depending on if you're in the coastal environment or maybe more offshore. Yeah. So, yeah.
In your first diagram, you actually showed anthropogenic forcing. And of course, as well, presumably, well, you didn't give any views as to natural events or recent phenomena. But this, I think modeling shows actually pretty large. But in and around Australia, can you kind of generalize that? Is there a common process that happens, or when you talk about winds, suddenly drop off? Is there kind of a way to identify more specifically the forcing of these events?
That's right. So when we start to look at the longer changes in these marine heat waves, we really need temperature data, not just over the last couple decades, available through or even 40 years through satellite products, but really extending back over the past century. And there are some products that can be used to kind of start looking at those background warming trends in these different areas. So of course, long-term warming in different regions is of concern, and certainly the Tasman Sea is one of those hotspots where warming trends are about 2 to 3 times the global average. But these marine heat waves, of course, are occurring on top of these warming trends. So it's an added component. Now, the question that people have been asking now is what will happen into the future with anthropogenic warming, and how will marine heat waves change? Will marine heat waves increase in frequency, intensity, duration because of long-term warming itself? Or will there be changes associated with like the climate modes of variability that can also contribute to that? So I think this is an active area of research, but certainly there is a lot of work being done in Australia to look at changes in marine heat waves, both using, for example, the latest CMIP 5-6 models, and to untangle what's happening in those.
What's the time? So I think we should move on, but thanks, Jessica. And I know there are probably a couple of questions in the chat, and there may be other questions in the room, but I'm sure you can get in touch with Jessica for more, or stick around afterwards. So I'm going to move on. So our second speaker, Matt, are you on the line?
Yeah, I sure am.
Yeah. Are you going to share from your end?
Yeah, I will give that a go.
I will stop sharing, and then
I will see if I can see. Let's see. There we go.
Perfect. So I'll just quickly. So Matt, we can see there. I'll close that down in a second. So Matt Moores is over in Wollongong. So Matt is so Wollongong are our major university partner within Tide. So UWA and Wollongong are the 2 leading universities in Tide going forward. Andrew, who asked a great question a minute ago, and Matt and David, I'm not sure, I assume he's online. David Gunawan is also the other CI from Wollongong. So Matt's going to talk today. I know, Matt, you're originally a Queenslander. I think, yeah, and then off to the UK for a postdoc, and now back here. I'm most impressed. I know it was Freedom Day, I think, for you guys on Monday. So I'm glad you dragged yourself out of the pub for long enough to. So Matt, I'll hand over to you, and yeah, please.
Great. Thanks a lot. So yeah, I am an investigator in the enabling theme, And the idea of this talk is I'd like to give an introduction to some of the methods that we use in data science and their role in digital engineering, particularly in this key issue of uncertainty quantification for inverse problems. And I'm going to be presenting some joint work with my PhD student here in Wollongong, Matt Berry, as well as his other supervisors, Mark and Brian, and our collaborator, Raymond Longbottom. So I'm going to start very generally with a mathematical model, and I'd like you to think of F as your favorite equation, whatever that might be. I'm going to show some illustrative examples in this talk, but these principles apply very generally across a bunch of different problems in oceanography, hydrodynamics, geotechnics, and structures, and so on. Now, this function f doesn't need to be available in closed form. In fact, it's often the solution to some kind of numerical model. So, for example, we might have a system of differential equations that we're solving numerically, and that then gives us our value of the function f. And as far as the parameters go, right now you might be tuning these by hand or selecting them based on values that other people have used in the literature. But you might be curious about whether we can learn these parameters from data. So that's the idea in data science. We're going to have some observations of the real world system at some times, or perhaps some spatial locations, or perhaps both. And we believe that these observations are going to match our mathematical description, but then this data are inherently noisy. So the first example that I'm going to show is this growth curve. And in this case, we can actually solve this equation analytically. And so this is our function f. And we're going to observe that at these time points t1 up to tn. And then the initial value of this function is just going to be alpha minus beta. And we have observations to go along with that. And we're going to assume a normal distribution so that we have additive Gaussian noise. And the unknown parameters in this case that we're trying to learn include the parameter associated with our initial value and the parameter that's associated with our noise. So it isn't just the parameters of our equation that we're learning, it can be other things as well, like tuning parameters. So this is the observed data. It's measurements of the length of some dugongs and then the age of those animals. And we can fit this model using nonlinear least squares. So here I'm using Gauss-Newton, but for example, you might be using Liebenberg-Marquardt or a quasi-Newton method. And the advantage of these deterministic algorithms is that they are very fast, and most of the time they do give us a pretty good idea of that mean function. So if we're mainly interested in the mean, then these methods are very good and very widely used. But there's a couple of drawbacks. One is that it's very hard to know if you have a convex optimization problem or not. And so your algorithm might only be giving you the nearest local optimum of the function. And so the results that you get are going to be completely dependent on the initial values that you use to start the algorithm off. The other issue, and the main issue that I'll be concerned with in this talk, is that those standard errors on the previous slide are systematically underestimated. So if we want to build confidence intervals for alpha and beta, those parameters, then our 95% CIs in a simulation study are only achieving about 83% coverage of those true parameter values. So an inverse problem is where we're trying to find the parameter values, and here I'm just using a vector theta, that are consistent with our observations y. And our physical model then doesn't need to be invertible. So although it's called an inverse problem, we never actually invert this function f. Although there is an issue with identifiability of our parameters, which can then lead to multimodality in our distribution of those parameters. But there is current research in how to address this issue of multimodality, and that's one of the things I've been working on, and I plan to work on in TIDE. And then our statistical approach is based on this likelihood function, where the mean of our random variable is just equal to the solution of our numerical model. And then we have some random noise that doesn't necessarily need to be Gaussian, although that's what I'm using in these examples, because it's certainly easier if we can assume the normal distribution, but we can do this much more generally. So we need to assign prior distributions on all of our parameters. Now I've chosen very simple priors here. So I'm specifying the boundaries of these parameters. So alpha and beta need to be strictly positive. So I'm specifying a prior on the log scale, and then gamma needs to be between 0 and 1. So I'm using the logit transform of gamma to go from a 0, 1 to a unbounded parameter space. And then here I'm just using these normal distributions to give very mild regularization to those parameter estimates. For a better way to set priors for these types of things, I highly recommend the paper by Lachlan and Ed in 2018, where they really go through in a lot of detail and use a really gold standard approach to set priors for mid-ocean parameters specifically. But in this case, I'm just using something quite simple as an illustrative example. Our posterior distribution for our parameters is then going to come from Bayes' rule. So here we have our likelihood that I showed earlier multiplied by our prior. And on the denominator, we have this horrible integral that we don't ever want to evaluate. So instead, we're going to use Monte Carlo methods. And the algorithm that I'm using in this case is a random walk metropolis. And so we start off our algorithm by initializing from those prior distributions that I showed earlier. And then we're going to propose new parameter values just using a Gaussian random walk on that unconstrained parameter space. In this case, we are solving our numerical model at every iteration. So if you're cringing at the thought of having to do that in a loop hundreds or even thousands of times, there are more advanced methods for mitigating this cost and reducing the number of evaluations of our function that we need to do. But in this simple case, I'm just going to solve the function. In this case, I know the analytic solution. So that's, for me, that's actually quite fast. This is a conditional linear model. So for the noise parameters, I can actually, rather than doing a random walk, I can do a different proposal from this inverse gamma distribution. And then I'm calculating the log likelihood using that mean, which is the solution of our function, and then that noise parameter. And finally, we're just going to accept or reject those proposed parameter values using this probability that we calculate here. So this gives us some Markov chains, and the advantage of this approach is that these Markov chains will eventually forget where they started from. So we don't have that dependence on our initial conditions that we have with those deterministic optimization methods. And we obtain posterior distributions for all of our parameters that encode not only our best guess at the parameter, but also the range of likely values for each of these parameters. Now, I mentioned that the deterministic algorithms are very good at estimating the mean, but you'll notice that this distribution alpha is very heavy-tailed and skewed, and our distribution of gamma is negatively skewed. And this has big implications when we're trying to estimate things like probabilities of exceedances and extreme values. It matters a lot what's happening in the tails of these distributions. And so these MCMC methods are a much better way of characterizing that tail behavior. From our posterior distributions, which are this blue line here, we can then get predictions for other values of, in this case, at other time points. And so these red dashed intervals are predictive intervals from our model. I'm going to sort of skim through the other example. Now, this is a more recent example of the use of these Bayesian inverse problems methods in an industrial context. So we have a chemical reaction here that's following this Arrhenius equation. So we have the change in mass over time. Then we have the change in temperature over time. And this is a controlled experiment. So we're increasing the temperature at some fixed rate alpha. The parameters that we're trying to figure out are what's called this pre-exponential factor A and the activation energy E in particular. Again, I'm going to be assuming Gaussian noise, and this variance parameter is also going to be included in this vector theta. So we have good prior information for the activation energy because this is physically interpretable, and we have pretty good prior information for our noise because that's mostly based on the instrument that we're using to make these measurements. But we don't have a good prior for this pre-exponential factor A. So instead, we introduce this other parameter that I'm going to call T max, which is the temperature at which the rate of the reaction is maximized. And this is an example where we don't have our function in closed form. And so we're using Runge-Kutta algorithm to solve our equation, given some proposed parameter values for E and A. And then we use that same random walk MCMC algorithm that I showed on the previous slide. And that gives us posterior distributions for that T max and for the activation energy. We then calculate A just as a function of those other parameters. And we also get an estimate for the noise. I mentioned calculating a function of our parameters, and this is another advantage of that Bayesian approach. So once we have our posterior distribution for our parameters of our model, we can then obtain predictions for any other function of those parameters that we choose to evaluate. And the main one in this context is the critical length of a stockpile of the material. That's in 1 dimension, or in 3 dimensions, we'd have the critical volume of material. And so we can evaluate that function for all of our MCMC samples. And that then gives us a posterior distribution for the value of that function, in this case, the critical length. So that's about all the time that I've got. But this is only the start of the types of Bayesian methods that can be used. In particular, David Gunawan in Wollongong has done a lot of great work in sequential Monte Carlo methods and also in approximate likelihood methods using things like approximate Bayesian computation and pseudo-marginal methods. And as most of us know, Andrew has done a lot of great work in spatiotemporal models and also in emulation of the function. So that's one way that we can reduce how many function evaluations or how many times we need to solve a numerical model in order to calculate our posterior distribution. So thanks everybody, and I'll take questions now.
Questions in the room or online? Yep, Ed.
Hi, Matt. It's Ed. Oh, great. Can you expand on the methods that identify multimodality and how to deal with it?
Matt, can you hear Ed there?
No, you might have to repeat the questions.
Sorry.
Hi, Matt, and how are you? Can you hear me?
Yeah.
Oh, good. I was just going to ask, I feel like now I'm speaking to people. I'm at the front of the stage with a microphone. Can you expand a bit on the identifying multimodality and the identification issues that you can get with more complex problems and the sorts of tools that you're using, A, maybe to identify them, but also B, then how to, dodge that problem by searching the spaces efficiently?
Yeah, so that's where what we want to do is actually combine the strengths of those optimization algorithms with our random walk Monte Carlo algorithms, because the optimizer is going to find the nearest mode wherever we are in the space. And so the method that I'm currently working on uses a parallel tempering approach where we're exploring parameter space And then every now and then we stop and optimize to find our nearest mode, and then compare that to a list of modes that we've already found.
Yeah.
And so that's one approach for identifying this issue of multimodality. And then you can design proposal distributions to jump directly between the modes that you've already found.
And you know, what gives you the notion, that sinking feeling in your stomach that you're not exploring it correctly? You probably know that feeling, right? You look at your MC algorithm. Is that what you're doing? And you sort of...
Yeah. So one thing that I didn't mention with this real world example is that we run multiple chains.
Yeah.
And the big giveaway is when like 3 of your parallel chains converge to one answer, and the 4th chain wanders off and gives you a completely different answer.
Yep. Okay.
And
I understand.
generally what you find is if you start an optimizer from those locations, you're going to get 2 different answers as well.
Yeah. Yeah. Quite. Thanks, Matt. It was a great talk.